of any functional neuroimager's existence. So as everybody who's spent any time looking at fMRI data knows, we have a lot of problems with head motion that typically manifests as artifacts often seen around the edges of the brain and particularly noticeable sometimes on the higher slices. And the common approaches in the field to dealing with motion artifacts are to do motion correction, to extract the plots of head motion over time, 3 translations and 3 rotations, and put them into the general linear model in order to capture variance due to motion that hopefully soaks up that variance so it doesn't show up in the predictors of interest. And then more advanced approaches that rely on things like independent component analysis to flag components that are related to noise, and again, use this approach of putting them in as predictors of no interest. So I spent a lot of my life dealing with motion artifacts as someone who's interested in studying action. So the first 2 years of my postdoc were full of data that looked like this, what we used to call voxel vomit. And we kept thinking it was head motion, and then we realized that it was actually mass motion, as we call it. So the mass of anything in the scanner leads to artifacts. So you can take a phantom, a fluid-filled sphere, and we did some things where we strapped on some bags of saline onto a hockey stick and moved it around in the scanner every 30 seconds. So we'd have the bags of saline on one side for 30 seconds, on the other side, and just alternating back and forth. It's important to emphasize here, this is a phantom. It's an inert fluid-filled sphere. It does not move. And yet, even though it doesn't move, if you look at the signals that are correlated with the position of the bags of saline, you get these artifacts. And those artifacts are manifest as spikes at the times of motion transition and as baseline shifts. So this turned out to be a big part of the problem we had with studying actions in the scanner. And moreover, it's not even like it has the same effect on every voxels. In other voxels, you just see these transient artifacts. And so every voxel has a different profile. And this illustrates one of the problems with things like including motion predictors in your model is you're trying to fit all of the different ways that it can be manifest across 100,000 voxels with a small number of predictors. And of course, it's different from voxel to voxel. So that's part of why that approach is incompletely successful. The other reason it's incompletely successful is that it actually screws up your motion correction algorithm. So if you take this data, remembering that the phantom itself never moved, and you run it through any of the standard motion correction algorithms, the motion correction algorithms try to move the phantom. And so you're introducing motion to something that didn't move. And so that's another part of the problem. And of course, in the more typical situation, you might have the head moving, which leads to the artifacts because the head itself has shifted position. Those are the things that motion correction algorithms are good at fixing, but it also leads to these mass motion artifacts, which motion correction algorithms do not fix. And so we did a lot of stuff with Ravi and Rob Berry looking at some of the distortions in the magnetic field that are related to these mass motion shifts. So that's part of the problem. So why is it such a problem? Well, these motion artifacts come across as having different temporal profiles in different voxels. So a small number of predictors isn't going to fix it. Another problem is that motion is often correlated with the paradigm. And that's certainly true in studies of motor control or speech or any of those kind of things. And it's also the reason we've got this renewed interest is we're doing these projects now on playing video games in the scanner like Pac-Man, and they're the most fun experiments ever, but they're so much fun you get really roused up by it, and even experienced subjects like me who are usually still as a rock occasionally have a little spaz because Pac-Man runs into a ghost in a tunnel that you didn't know was there. And so we've had a lot more problems with motion artifacts in that paradigm, and so it would be really helpful if we could clean that up. And then another thing which Ben and his colleagues have talked about in the papers is that a lot of neuroimaging these days relies on functional connectivity, resting state being the most common. And in those cases, you want to isolate connections that are due to legitimate functional connections versus correlations that are just driven by correlated noise, say breathing artifacts and things like that, motion artifacts. And so because of that, that's why some of this multi-echo stuff is of interest. I think Suzanne's going to get into the physics more, but I've just got one slide here to illustrate the gist of the idea. So we know when we look at how the T2 star signal, the bold signal, decays as a function of time, that you have different decay rates depending on how much deoxygenated hemoglobin is in the local environment. So if you're in a baseline state and you have a lot of deoxyhemoglobin, then the signal decays quickly. And if you're in a task condition and you've got your blood vessels are dilated and you're flushing out all that deoxygenated hemoglobin, then the decay rate is slower. And so what we're really interested in, what bold imaging picks up on, is the difference between the two decay rates. And typically in good old-fashioned imaging, what you do is you just sample these differences at one point in time, the time to echo. And you try to pick that time to be the time when you've got the maximal difference based on what we know about the bold signal. You've got the maximal difference in the bold signal, because that's really what you want to isolate. So the core idea with multi-echo imaging is that rather than just sampling this decay function at one point in time, you can sample it in multiple points in time. You can do multiple echoes or multi-echo. And so, for example, if you capture an echo as soon as possible, then you're not going to have very much bold signal in that echo. And yet any noise components that are related to things like the participant moving are going to show up in the early echo and the late echo, but the bold signal is only going to show up in the late in this kind of optimized echo. And so if you get the noise plus the bold in this one and the noise without the bold in that one, then you can do various strategies in order to effectively compare the difference between them and get the bold by itself. And those methods differ in their sophistication. And I think Suzanne might talk a little bit about the more modern stuff. But before we get to the modern stuff, I just wanted to talk about the paper that originally got me very excited about multi-echo stuff, which was using, I guess now, Ben, you sort of said this is a bit of an outdated method, but nevertheless, even the outdated method showed a lot of promise for cleaning up data. So that's what we'll start with. So what Ben and his group did was they put people in a brain scanner and they had a protocol that looked like this. So they have some baseline conditions here in white where the participant isn't doing anything. And then they've got other conditions where they're showing a visual stimulus, a flickering checkerboard. So both these light gray periods and the dark gray periods are all periods where there's a flickering checkerboard. But they also deliberately made the participants move in every second epoch. So in this epoch here, the flickering checkerboard was on and the participant didn't deliberately move. But in this one, as soon as the flickering checkerboard started, I forget what the subject did. They tried to tilt their head forward or something like that and hold it there or move it around and then go back to normal once the flickering checkerboard turned off. And then we've got one without motion, one with motion, without motion, with motion, and so on. And you can see when you, this is the motion correction plots, and you can see that indeed there's some drift throughout the run, but the participants were indeed moving when they were supposed to be moving. Is that clear? Are there any questions? Okay, so that's the paradigm. And so what you would hope, if you've got legitimate activation should have a bold signal that peaks anytime there's a gray thing going on, and artifacts should only appear in the dark gray periods. So what they did with this was they went to this first echo and they just extracted a time course, I think for every voxel of the first echo time course. No, not for every voxel. It must have been at a higher level. And then they put in the time courses for the first echo as predictors of no interest. Actually, was it voxel-wise? I can't remember now. Anyway, you put in the first echo time courses as a predictor of no interest. So that should model out any of the artifacts that are related to the motion, leaving you with a more pure example of the bold signal. And so what we're looking at here, this is kind of a nice way to look at artifact filled data. One strategy that you can use is to focus on the difference between type 1 errors and type 2 errors. So there's some areas for a flickering checkerboard, you expect legitimate activation in the visual cortex and not much activation elsewhere. So you don't expect activation in the frontal lobes for visual stimulus. So all of these blue voxels here are clearly artifact. And so you can look at the effect of these different procedures on legitimate signal or type areas that would be prone to type 2 errors, or you can look at garbage signals, which would be type 1 errors statistically. So if you extract the time course from visual cortex here, you can see that you do indeed get these fluctuations that are correlated with the paradigm, but they're pretty garbagey in these epochs where the participant is moving. And so you don't get that clean a signal. And if you do the good old-fashioned approach of just putting in the motion parameters as a predictor of no interest, which is this curve here, you can see that it doesn't really solve the problem. In theory, it should. In practice, it doesn't. You've still got time courses that are really garbagey when the subject is moving. But when you use this E1 situation here, this is when they use the first echo to as a predictor of no interest to correct the signal. Then you can see you get a time course extracted out of visual cortex that looks like what you would hope it should look like. So you're closer to the ground truth with the first echo correction than you are with the uncorrected data or the conventional correction with the motion parameters. And similarly, you can look at this bit here, which is the garbage activation, and you can see that it shows up as deactivated when you do the statistical test for visual cortex activation. And that's because you've got all this schmutzy stuff coming out of the periods when the participant is moving that's leading to false positives. Again, if you try to correct it with motion parameters, it maybe tidies it up a little bit, but it's still pretty bad. Whereas if you clean it up with the first echo correction, you get something that looks just like a noisy flat line, which is closer to the ground truth. So long story short, this echo correction has the benefit of preserving clean activation where you should see it and damping down erroneous activation. And you can see that here in these glass brains when they make a map of looking for areas that are correlated with the flickering checkerboard. In the uncorrected data, you see you miss out a lot of the occipital cortex where you should be getting a legitimate signal. The typical motion correction helps a little bit, but it's still pretty bad. And the echo correction helps a lot. So that was the paper that got me really excited about this. And several years ago, and we tried to start looking into this, but I think at that time we couldn't get the right pulse sequences for the scanner, and it wasn't clear how you would analyze the data. And so we kind of left it on hold for a while, but it seems like these techniques have really matured over the recent years, and other people have started using them at Western. So I think we're ready to start doing it. And Suzanne, I don't know if you have any slides prepared about the other benefits like susceptibility dropout and stuff like that?
I do. I have stolen an image from the Kundu et al. Review paper, which shows very nicely that you can claw back some signal. Mainly focuses on the inferior frontal, but it's pretty illustrative.
Okay, well, so maybe I'll just ask if there's any questions on this stuff. And if not, I'll pass the torch. Any questions or comments? Okay, I'll pass the torch to Suzanne then, as soon as I figure out where the button went to stop sharing.
Okay, so I'm a physicist by training, for those of you who may not know. So this is going to be slightly more graphs with some pictures, a few equations, but hopefully enough and simple enough to sort of get you to understand what multi-echo actually gets us and how sort of the current denoising sort of pre-processing pipeline works at its most fundamental level. Sort of just, I found this sort of illustrative example of just sort of why using a single echo time, which is what the vast majority of the field does right now, may not be actually the best option, because there are both echo time dependence within the brain. So, not every region, responds, or you won't get the same signal from every region at a consistent echo time. And then also T2 star, which is what our bold signal is related to, that also varies throughout the brain. So the more that you can sort of put together multiple echo times, actually the better that this signal gets and the more refined that it gets. So I'm going to cover basically what is multi-echo EPI. Jody sort of covered a little bit of it and how it differs from a single echo EPI. Basically the two main reasons why you would want to consider this, how you go about analyzing this, and then just a couple things to consider along the way. So single echo EPI, as Jody sort of showed, we get this exponential decay. This is T2 star decay. And basically in a single echo EPI, we pick some echo time somewhere between 30 and 60 milliseconds, sort of as a happy medium to try and capture as much signal from as much of the brain as we can. And we go ahead and we, run our sequence, excite our pulse, let it decay to the echo time, and collect the signal. So in multi-echo EPI, we basically we will still collect our sort of optimal bold echo, but we will add echoes either before and after to, basically collect further snapshots of the data. A lot of the sequences that I've seen published in the literature tend to just do 3 echoes. So you have an early, an optimal, and then a late. Basically, any echo that you put in before the sort of nominal optimal echo or echo time of the sequence is free. So this will not, anything that comes between sort of the start of the sequence and this blue echo time won't extend the timing of your sequence. This is all dead time in the scanner. And as the scientist I used to share an office with said, that dead time is bad in MR sequences and you should try and fill it with something useful. Echo times that you start putting in after the optimal echo time of the sequence will extend the timing of your sequence. So be careful about, it potentially seems tempting that you want 8 echoes, you want as many as you can collect, but this will, things that come after this blue echo time will slowly start extending your sequence. From what I understand from Joe at CFMM, we do have the multi-band version of the multi-echo sequences, so timing in terms of extending your TR is not as sort of detrimental in terms of adding, an extra echo in the late. So in practice, what this looks like is for every sort of bold time point that you acquire, you're going to get sort of a volume for each echo time that you acquire. So early echoes, as you can see here for this upper one is 3T data, this lower one is 7T data. You see that we get, high SNR but low contrast. So you're not seeing any sort of gray white matter, but you are getting a lot of signal out of this. Late echoes in contrast, so echo times that are coming after sort of your optimal bold echo time will sort of be the reverse. They'll have low signal to noise ratio, but high contrast. So those are kind of the different, this is what you gain by doing early echoes and then also what you gain by doing late echoes. So reasons, basically there's 2 main reasons to consider using a multi-echo EPI sequence. Jody nicely covered the motion one. So artifact removal, this will cover head motion, physiologic motion, scanner noise, a lot of stuff that's collected on a T2 star sequence, but isn't related to the bold sequence. And then the other one that you'll see in an image of in a couple slides is signal recovery in high susceptibility areas. So regions that you would normally see signal dropout on in your bold images, using a multi-echo sequence and the weighted averaging of the multiple echoes allows you to claw back some of that signal. So that's kind of acquiring the data. We have ready-made sequences at CFMM, so piloting itself is largely trying to figure out what are the optimal echo times that your study needs. So in terms of processing multi-echo data, there is currently one main pipeline called Tadana. It is a BIDS pipeline, although Ravi just pointed out that there's a group that is slowly developing a toolbox called FMRY, as in WHY, and there's a link at the end of the presentation that is looking to be an SPM12 MATLAB based, that they will be reprogramming the main parts of Tadana for MATLAB based analyses. I took a look at the toolbox. They don't have the multi-echo code yet. So, but it's sort of on their to-do list and main feature list. So the Tadana pipeline itself can be run standalone on BIDS data, and it is integrated into fMRI prep. I believe it's from version 1.5 and above. It may be 1.4 and above, but in the more recent versions. So at this point, I will say I have run this pipeline once. I have read through the documentation a few times, so please forgive me if I don't know all of the specific details and questions that you may have. But basically, the main steps of this pipeline is first to optimally combine the echoes. They then use a PCA step to identify thermal noise. Then they use an ICA step to remove any echo time independent noise. And then there is an optional step to use a global signal regression to remove any remaining spatially diffuse noise. So the first step in terms of optimal echo combination, it uses a weighted average. So it's not that you just, average all the signal, divide by the, add up all the echo time images and divide by the number of echoes. They are weighted in terms of the echo time, so that echoes that are close to the optimal bold are weighted higher than echoes that are further away from the optimal bold time. So that in this situation, you don't either have an early echo or a late echo dominating that weighted average. But you can see for both 3T and 7T, even with just 3 echoes, you are able to see, once they've been optimally combined, significant signal recovery compared to what you would have just gotten from a single echo in this sort of inferior frontal, orbital frontal area. So this is one of the reasons to do this, but there's not been a lot of, there's been a couple studies looking at more subcortical regions to show that yes, doing a multi-echo approach, also will increase signal, but there just hasn't been a lot of studies to basically say that yes, this is definitely the best way of regaining this signal, but it's a good one. So sort of going to skip over the PCA because the PCA is basically thermal noise is Gaussian and bold signal isn't, so it's a pretty simple split between those two. But we are going to talk about sort of the main thing that the Tadana toolbox does, which is to classify signal in the brain as either being echo time dependent or echo time independent. So little bit of math. So MR signal equation, basically it is just an exponential decay. I'm going to be using R2 or R2 star for most of this, just because that's what the Kundu paper uses. So there's some consistency if you've read that. But R2 star and T2 star are just reciprocals of each other. So basically we have this exponential decay. You can use a linear approximation via Taylor expansion to simplify it into this equation here. And basically this simplifies, and the main thing is it simplifies into two independent terms. One of them is dependent wholly on the base signal, and the other one has this R2 star and echo time dependence to it. So this is a similar graph to what Jody showed in her brief presentation. And if we focus just on this delta S naught over S naught, so the baseline signal change over baseline signal, if we have some rest and activation, we get a difference, which is also an exponential decay. And if you plot this in terms of echo time, it's basically a straight line. So this term has no echo time dependence. Whereas if you have two voxels or one voxel at two different time points where there is, an R2 star or a bold signal in it, you'll see that if we follow the same progression, that there is an echo time dependence on this. So what the ICA is looking to do is figure out whether your signal, sort of shown in gray here, looks more like this signal change predicted by the S naught, the baseline signal, or whether it looks more like the signal change for a voxel that has a true T2 star or a true bold signal. So obviously, we're never going to be in a situation where a single voxel is going to be uniquely classified into one of these categories. So the Tadana toolbox uses a pseudo F-score to predict how much the signal in a given voxel either matches the S naught, so the TE independent, or the TE dependent. So they assign either, there's a kappa score for how much it matches the T2 star, so the bold, and then a rho for how much it matches the S naught. And there is some cutoff, but I couldn't find it in the Tadana documentation of where exactly that cutoff is set, of how they decide. But obviously there are going to be lots of voxels in your brain that are mixed, that have both artifact and signal in them, and the toolbox is not going to make a perfect distinction between the two. There will be a gray area where you're either going to cut off voxels that have signal in them because they're more dominated by noise, or you're going to allow more noise in because there's signal in the voxels. So that's basically what the ICA is going to do in Tadana, and then it's going to regress out anything that's classified as noise, and then it will write out your time series again.
So Suzanne, so you're saying so it regresses it out, so you don't totally, if you have a voxel that's a combination of signal and noise and more noise, you don't throw that out completely, you still just try to clean it up, is that right?
So at a certain point it will throw out stuff, because I believe there is a cutoff in terms of these kappa and rho scores. But the Tadana documentation isn't sort of super complete in terms of sort of all of the interior decision making that it's doing in that ICA. But depending where that cutoff is set, much like ICA Aroma and ICA Fix use spatial templates for doing spatial matching of whether or not it's, signal or noise, This one is actually using this comparison between these two curves of whether or not it's signal or noise. And there's always some decision point for that. And so if you set the decision point too strict, then you could be removing signal because you've got voxels that have signal and noise, and you're like, I absolutely don't want any noise voxels in, and then you could be losing signal. You could set it, or it could be set more relaxed where you have voxels that have both signal and noise, and you're going to allow some of that noise back in because you want to pull the signal as well.
Right, Suzanne, just correct me if I'm wrong. So the ICA works on the time series of different echo times of a single voxel. Is that right?
So the time series, yeah. So it will, because you have multiple echo times, now you can estimate that decay curve.
Yeah, but you have the multiple echo times, and then you have it for each TR, and you do an ICA on that.
Yeah.
With the idea is that whatever changes the intercept of that decay, namely the S0, is going to be independent of the thing that changes the T2 star, basically.
Yeah.
Okay.
That is the underlying.
Okay, so why not stop there? I mean, like, it seems like, okay, once you have the ICs, the independent components, why not just use them? Why this like funny thresholding and so on? Why not?
I think because they wanted to be able to output time series that then people could put into.
Yeah, no, that's why not. Like, once you have the ICA, once you've done the ICA, you have the two components.
Yeah.
I mean, you have the cleaned up signal basically, and the cleaned up and the estimated noise one. You could just give that to the user and then let them make their own decision on thresholding and so on.
I didn't write Tadana, so I can't speak to them.
Is this something that Benedict, did you develop this pipeline, or do you know the internal guts of it, or?
Neither, actually, no. I mean, the idea was really Pantik's idea, what it was in the NIH with Peter. So he came up with this, and that's what he published, first in neuroemission. And this.
So you have your own pipeline to clean up?
We don't actually. No, we don't actually do much multi-echo at all. And I'm encouraging people to actually look into the Tadana for sure.
I see. Okay.
I mean, the few people that we have that do multi-echo,
and
they've been quite happy with it, especially since it's been wrapped so nicely with all that Python. And so on. So basically, the initiative from Elizabeth, that's been a great step forward.
Okay.
So in terms of what the Tadana outputs, it does output Yorn a lot of the intermediate steps. So if you don't want the final output there, you potentially can pull back and find an intermediate output. So it doesn't hide them all, it doesn't delete them all. They are given to you. Sort of the main three are you can just have the optimally combined time series with no denoising. So if you want to go down your own route in terms of how best to denoise, it will just give you the weighted average. The one that they recommend is the denoised time series. So this is the one that's been optimally combined, been through the PCA and been through the ICA. And right now, according to everything I've read on the Tadana website, this is the one that they recommend if you're going to be running first and second level analyses. They also give you one that they call the high kappa time series. Basically, this is a highly denoised time series. So basically, this is going to really err on the side of only accepting things that they really think are signal and getting rid of everything else. It also doesn't include any sort of thermal noise, and they don't recommend this for analysis. I couldn't read any place of why they output this, but someone may have wanted it at some point. And then if you do the optimal removal of spatially diffuse noise, then depending on whether or not you use a global signal regression or a T1 corrected global signal regression, then you'll get the respective extra denoised time series out. So as I've said, I've only run this once, and I've looked at this particular, the recommended one. So I can't speak to any sort of, oh, I've definitely run a first level analysis on this, and I can tell you that this one definitely seems to work better than this, this output file. And just a couple resources. So the Tadano Read the Docs is this website, and then this new one that Ravi sort of told me about, which is going to be a MATLAB SPM 12 more compatible. That's the Read the Docs for that one. But as I said, I couldn't see any evidence that they actually had the multi-echo code up and running. So that is as far as I've gotten in my sort of learning and presenting of multi-echo. So I guess if people have questions, we will go ahead and take those.
Thanks, Suzanne.
Yep.
So what do we need to do to start playing with this? That's my big question. Do we have, are the choices of sequences, how different are they between those of us who want to use it for motion correction versus those who want to use it for susceptibility recovery? Can we go into the scanner tomorrow and collect some data, or is there anything we need to sort out before we do that?
Yeah, you can collect data tomorrow. It's there's no problem doing that. There's plenty of different data sets we can do. What you really have to define is you have to work with the trade-offs with the sequence. So, I mean, if you want to do something that's high resolution, sub 2 millimeter isotropic, I think you're going to have a little bit of trouble. You might have to accelerate a little bit too aggressively.
So take our garden variety fMRI these days, which is 2 millimeter isotropic, TR of 1, multiband. Are we going to take any hit in the temporal resolution to do multi-echo with something like that?
Yeah, I think so.
We are going to take a hit?
You are going to take a little bit of a hit, especially at 2 millimeter ISO. I think you're getting right at, unless you start accelerating, right? I mean, there's no free method lunch here, so you're going to take a little bit. It's just, I mean, it's a matter of using a higher grappa factor. So with that, things are going to get a little bit noisier. I mean, Ben's going to have experience with this. I mean, we haven't done a lot of multi-echo. I mean, it's easy to put the protocol together, but I mean, there are going to be trade-offs.
So can I get a sense of the trade-off? I can go to 3 millimeter. I can go to 1.5 second TR. Are those?
I think at 3 millimeters, I think 1 second is probably doable, but you may, it's sort of the brain coverage that might be what you're giving up a little bit of. At 3 millimeters, you could probably still do whole brain at 1 millimeter with 3 echoes.
I don't just to understand the trade-offs here. So multi-echo just works with multi-slice and in-slice acceleration basically smoothly. There's no extra interaction cost between the two, right? Or does it get in the way of?
No, there should be no other interaction there.
So k-space undersampling and multi-slice is totally fine. That works okay. Or?
Just the regular artifacts that you have with slice and in-plane acceleration.
Sure. Yeah.
Yeah, I think the main limitation, if I may chip in here, is you mainly the total acceleration. You don't want to push beyond, say, 8 or something like that.
Oh yeah, I mean you don't want to. Yeah, you don't want to be there anyway, I guess, right?
And even if you say, okay, 3 millimeters or even 3.5 millimeters is enough for you at 3 Tesla, you do need some grappa acceleration in plane in order to accommodate the multiple echoes at reasonable echo times. So that means you're already giving up a factor of 2 of your total acceleration capability to be able to do multi-echo, which then limits, say, your multiband factor to a maximum of 4.
Oh, I see. Okay.
Right? So otherwise, I mean, you could do the crazy thing like I do in a human connectome project and do like a factor 8 slice acceleration.
Yeah, I mean, for multi-echo to have really like beneficial circumstances at 70, say, so normally you have an echo time of, what's our standard echo time right now on a 70?
About 20 milliseconds.
20 milliseconds. And so which echo times would you recommend, Ben, at 70? And how many?
Well, yeah, recommending is one thing, accepting is another. I think, I mean, the constraints, they're really, I don't know what we ended up with. We are running a pretty nice protocol at 7 Tesla actually with 3 echoes. I can dig that out for you. I don't know.
So like, 7, 20, and 40 or something.
No,
How
don't
high?
get that low, because you don't want to have. I think you don't want to compromise the spatial resolution too much. I mean, you want to have at least 2.5 millimeter in plane resolution, at least at least that low resolution.
Yeah. So the Kundu.
So you go. What's your highest echo time? Then you go to basically.
I would have to dig that up. I don't want to lie to you now, but I think it probably puts you sort of to 45, which is probably pretty sweet echo time to be at if you want to do sort of parietal and anything occipital. Right, the T2 star is pretty long. That's 7 Tesla. People forget. But it's not going to buy you any benefits then for BrainsCAN or sort of these nasty regions that are most affected by dropouts and so on. But let me look this up actually and put it in the chat if I find it.
I'm just trying to think of the best game plan for 3T. There's a couple of options we could, and I don't know how much we need to pilot different sequences or if it's pretty clear what we should start with. Doing some things like we could resurrect the old bags of saline and try a phantom. We could try to do something like that paper that I talked about where we make the subject deliberately move and just see how much we clean it up. Maybe we can book some scan time soon and just play with some things. Are there multiple sequences we should try, or should we just go with one?
I'd stick to the multi-band. I mean, if you're going to go for just a bread and butter single echo, or not single echo, or non-slice accelerated type of sequence, it's just going to be too much trade-off, right? I mean, your TR is going to get too long.
Okay. Ravi, I was just looking at your paper with Olivia about the phase stuff, because that's another option to reduce the motion artifacts. I don't know if you have any thoughts on which would do better, or in theory, could they even be combined at some point?
Well, they certainly could be combined. I don't know if which one is better. I mean, phase has the advantage that it requires no compromise. So if you have a wave KP or a multi-band or whatever, you just acquire or you just save and reconstruct the magnitude and phase. So from that perspective, it's nicer than multi-echo. Fundamentally, whatever you see in the phase is stuff you don't want. So you could come up with tools like either the ICA or simpler things, actually, which regressed out stuff that you find in the phase from stuff that you see in the magnitude. You will be disappointed because you will lose some of your magnitude signal, because at 3 Tesla, there's still a fair amount of large vein signal, and the phase approach will remove that. There are probably some clever ways around that, in that you could blur the phase, because we're not looking for really fine scale stuff. We're looking for, say, motion or artifacts on the level of a centimeter or something like that. So if you blurred your phase and then regress that out of a equivalently blurred magnitude, and then went back to the high resolution version, you might be able to actually keep your large vessel signal, which is ironic, but may be helpful in cases where you don't care about super high spatial resolution. And of course, you could acquire multi-echo in complex value acquisition, and then you would have phase for every echo and magnitude for every echo, and there are probably clever ways to deal with that as well. It certainly adds phase corrects the through space, or at least detects the through space changes that you see, like the saline stuff that you showed that we did with Rob Berry way back when. You would get B0 changes, and you could regress those out before you did the motion correction. And so, you know, I think some hybrid is probably the best approach, but you know, there are a lot of parameters, so I don't know necessarily what would be the best.
And how plug and play is the pipeline for the phase regression stuff now?
It's not very at the moment. It was for a while until we upgraded to the Terra platform on the 7T. So it was only ever done on the 7T. So it was under VB17 originally, and we were able to export that to the what were we, a Gadgetron, I think we were using for doing the recons. That exporting pipeline broke when we became a Terra or a MRI Plus. But Martin has come up with a simple solution using SVD, which Brett is going to work on. One of my, well, you know Brett. So Brett's going to work on that to determine how many dummy or steady state images you need to make that work. And then it's completely transparent. There's really nothing to do. That the data that comes out will be magnitude and phase, and you can use it as you wish. You can discard the phase, or you can analyze the phase. So there's no processing pipeline, but it'll be DICOM data, and then we can go from there, basically.
So Jorn, you had a question?
Yeah, I had a question to Benedict, I guess, mostly. So for the multi-echo stuff, we played around with different echo times for deep cerebellar nuclei and, well, globus pallidus. I mean, basically nuclei that contain a lot of iron, where the T2 star drop-off is very, very fast, and to get some good functional signal. And obviously, you're kind of like where the optimal bolt would be for a single echo sequence would be shorter, right? I mean, you would want to go a little bit earlier. In this with a multi-echo, it seems like a good. I mean, it seems like you should be able to get this for free. But with the current pipeline, would you need to optimize them differently than in these structures that have very fast decay rates, or to get good bolt sensitivity?
I think it should be all right and should fall out of it. I mean, there is this paper by Saskia Bollmann 2 or 3 years ago. I mean, she did some pretty deep brain activation stuff. I don't know where, I think basal ganglia even.
Yeah, globus pallidus has a lot of iron as well.
Yeah, and so she did it there, and she found multi-echo to still be advantageous in those areas. And I think they did not have a resolution that was any higher than 2 millimeters.
Yeah.
It honestly surprised me what she found. I would have thought you'd be better off with a thin slice, you know, and a decent in-plane resolution and single echo, and then just do like proper physiological noise correction and all the blah, 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 instead of compromising resolution so much and then going for multi-echo. Because mind you, I mean, if you compromise spatial resolutions, your voxel goes like with a power of 3, right? I mean, if you go from say 1.5 millimeter isotropic to 2.5, I don't know what factor that is, but it's a pretty crazy factor, and the physiological noise goes up a lot. So I was a little surprised, but I mean, check out that paper. It's by Saskia Bollmann.
Bollmann, B-O-Y.
B-O-L-L. Boll.
Oh, Bollmann. Okay, yeah.
Yeah, very German.
Yeah. Bollmann. Genau.
Yeah,
Huh. Okay, that's interesting. Yeah.
The question.
So, but you, I mean, like in the raw EPI in the images in the paper, there's clearly more signal there, right? Because it takes the early echo times. Yeah, I mean, so do you think the bolt sensitivity should be the optimal thing? Should be close to optimal then in the bold sensitivity, or?
I mean, it seems quite okay. I mean, of course, you're losing a lot of sensitivity by sampling at a too short echo time. I think this is sort of the problem that people run into a lot back in the days when they scanned at 1.5 Tesla. They really wanted to reduce the TR, and then went down to sort of echo times of 35 or 40, and then losing half the sensitivity because they're on the sort of steep part of the bold sensitivity curve, which becomes then really nice and shallow. I mean, you lose very little by using the longer or too long echo time.
I see, yeah.
But you lose a lot more by having one that is too short. So that said, I think you're doing pretty well with a multi-echo protocol, which gives you a shortish echo time and then sensitizes you or makes you optimally sensitive to what's going on in those more strongly, those brain regions more strongly affected by homogeneity. And then having 1 or 2 echo times that lend you slightly longer than what you would normally use to pick up all the activation in the rest of the brain that is not affected by homogeneity. So I think you're not losing that much. And then one more consideration is actually that if you use multi-echo anyway, and that gets a little convoluted, that argument, but I think it still holds true. You're anyway forced to use a somewhat compromised spatial resolution that isn't as high as you would normally go for, which means your voxel is larger, which also means you have more physiological noise, which also means that you are not as compromised by, say, using grappa 3 instead of grappa 2. Because that extra image noise that you're getting in, or what sort of pseudo white noise, is not actually dominant. It's still the physiological component that is dominant. So overall, you're not losing as much as you would think.
I'm surprised a little bit about that. I would think if you had motion or deep breathing or something like that, you know, the grappa artifacts can get pretty awful. I mean, even if you use, you know, Fleet as your original.
Yeah, that stands and falls with the reference data, I think, more than what happens in the time series. I think that you really need to figure out. I mean, you need to have a good reference, but I think that is true in any case. I mean, with or without multi-echo, you do have to have a good grappa reference. So look at your single band images, always the single band reference images. When they come in, look crappy, just stop and restart your scan. For those who know what I'm talking about. It's a great feature to be able to check those out.
So you mentioned you weren't actually using multi-echo that much. Any particular reason? Is it just lack of pipelines, or?
No, I was just tired to kind of keep talking against those pushy people in my environment that, you know, went more and sort of follow whatever they do with the Human Connectome project and be very pushy on the slice acceleration when that started. And obviously there was no sequence available at the time. You know, I had to sort of multi-band my own multi-echo sequence, which I did with quite some effort, but then people said, oh, well, but then you can't scan so fast. And I had other scientific interests. I honestly just didn't want to push as much internally, so it became a bit pointless. But I mean, now people are sort of adopting it slowly, maybe also because it is now finally part of the Minnesota sequence, which does let you do multi-echo, right? So it's actually very convenient. It's just, you just have to increase the number of contrasts and that's it. It's very nice. It took them 5 years to finally listen and put that in, but they did, and it's great to have it. I think it makes it very accessible to everyone now. And I'd even say almost at 3 Tesla, there's almost no excuse for not using multi-echo, because then it really comes for almost free. Now at 7 Tesla, it's really, you have to think about, you have to have a good cause, I think.
So yeah, I mean, Ingrid
had a question.
Ingrid has her hand up.
Yeah, hi. I'm wondering if one is willing to accept a long TR. So a lot of the work that my colleagues and I do is auditory, and we squirt in sound, try to get the brain in sort of a steady state and image 4 seconds later, and using kind of a sparse design. And there we can accommodate, I think, relatively long TRs. Does that help with the resolution compromise? The spatial resolution compromise? I mean, can we go for smaller voxels with a longer TR? Maybe this is a naive question.
No, it's not naive, but it's. I wish I could say yes, there is a way to compromise, but no, there isn't really. I mean, it's really. I mean, you have to. The compromise in your spatial resolution really comes from having to accommodate multiple echoplanar readouts and still getting a reasonable echo time. So no, there isn't anything you can do really.
Okay.
Dumb question, does it make it any noisier to collect multiple echoes in terms of those who do auditory and might want to salvage susceptibility zones? I don't know what causes the noise. Is it in the echoes or?
I mean, the echo trains themselves are essentially the same. You just have 3 times as many. So I don't think the noise is the magnitude of the noise isn't going to change that much. Maybe the duration is going to change a little bit.
Yeah, I mean, you accelerate more also, but overall each readout becomes, so the amount of switching between the excitation becomes more. I'm just thinking it does sound a bit more aggressive than what a normal sequence would sound like.
Yeah, I mean, I guess if you increase the bandwidth to compensate for your echo train,
Exactly,
getting longer, then you are making a higher pitch for sure.
Right.
Which is going to be the temptation. I mean, you're going to have to do that, right? To squeeze all those echoes in.
True. I would say subjectively it is, and we never measured it, but it is actually, you end up with protocols that sound louder or more high pitch.
But otherwise, theoretically, I mean, like what Suzanne said, that, the early echoes come for free. You could get earlier echoes shorter than your current echo time for normal. You just take your standard sequence that you have and squeeze in earlier echoes, and you wouldn't pay any price. Is that true, or?
No, not quite. No, you would generally try to fill as much of the time to sample anyway. So that means at 3 Tesla, you probably use a slightly lower acceleration factor than you would for a multi-echo protocol, or you would make a resolution higher simply because you can, or something like that.
Because you sample anyway the whole.
Yes, you would. Not all of it, but you would use a smaller partial Fourier factor, stuff like that. I mean, you would try to find ways to sample as long as you can.
Okay.
Okay. Any other questions? Okay, so Joe.
So coming back to whether we want to team up to try to industrial strength, try it out here as a group.
Yeah, I mean, I'm happy. So I'm thinking for my group, what I'd like to do is do the bags of saline on a stick and do a replication of the experiment that I talked about from Ben's group, where you do flickering checkerboard and move the head. And then I don't know if there's if that kind of data would be optimal for. So there's other people like Ingrid who might be interested to see how much it cleans up the auditory cortex. Wouldn't help in terms of the signal there, but we could at least look at the images and see how much we recover. And then I don't know with you, Jorn, if that data would be of any use with the.
Well, the bags of saline experiment, we did that as well with arm movements, right? And we did after I talked to you back then at SFN, that's a pretty convincing experiment. So yeah, redoing that is great. Yeah, I mean, the question is for us right now for 3T, that would be useful. I mean, the key thing is like whether for the current 70 project, but there we want to do something pretty high res, like 1.5 millimeters isotropic, which I guess would be, Benedict, would be too much pushing it, right? Probably, or you would compromise too much on overall.
I don't think you could really. Yeah, no.
So 2.5 millimeters isotropic is what that was a 3 Tesla sequence. No, 2.2 was a 3 Tesla. Was it 3 Tesla or 7? No, that's 7 Tesla. I see.
So that was 2.2 is what you can quite readily still do with 7 Tesla. I mean, mind you, if you're worried about sort of through slice dephasing, so dropouts if you wish, you could still, of course, use as thin a slice as you like, right? So you compromise the in-plane resolution, but you can still reduce the voxel size or voxel volume to counter physiological noise by saying you go for a thinner slice. But that would make your TR longer again.
Yeah.
On top of you not being able to use a high multiband factor, maybe.
Yeah.
Because you're already investing some to grab a 3.
Yeah. But 2.2 is kind of an okay place, certainly for cortical imaging. Cerebellar one,
yeah,
it's not pushing it, but if you go down to 1.5 and you get crap signal, that's that's another issue, right? And then you're also not happy. So yeah. So yeah, Jody, you would mostly try it on the 3T for starters, or?
Yeah, I think I just want to start with 3T in part. Well, for two reasons. One is when we get into the doing hand actions, that's really hard to do in the 7T because the bore is too small.
Yeah, yeah.
And then also the big project I think that would benefit the most at the moment is Pac-Man, which at some point we might want to port to 7T, but I think that there's enough to do at 3T just to figure out analysis and so on.
I mean, if we could set up a 7T pipeline, so something like the 2.2 millimeter protocol on the 7T, and try it out and see if it solves some of the susceptibility problems and maybe even lack of signal from the dentate problems, because 2.2 millimeters is still okay for the dentate. It's like the upper boundary. We could try it out on the 7T and just run our standard experiment, the multitask one, on it, and just compare on the same subject.
Yeah, another question. I think this question's for you, Jorn. Do you see much cardiorespiratory pulsatile artifact when you image the cerebellum?
Oh, terrible. Yeah, it's awful. There's 50, I mean, in the anterior brainstem is about 50% of the raw signal that you can explain with the first 3 harmonics of retrocore, right? I mean, it's massive. Yeah.
Okay. How do you get rid of it?
We're working on it. It's a constant struggle. I mean, the interesting thing is it's really bad once if you're out in the arteries. Once you're actually in the tissue, it becomes less bad, and just regressing it out is kind of sometimes a zero-sum game. So, it's, I mean, it's still an interesting question of how to do it, but I mean, there's no free lunch, unfortunately.
Is measuring the heart with EKG something that you would do?
Well, we're trying to. Suzanne, did you talk to Joe about cardiac?
I did. Yeah, I emailed Joe, and he basically said that the EKG wasn't the best on the 7T, that you could wind up with more problems in terms of just not having good signal.
Yeah, so fixing the PPU better is finding a better place. So we have still trouble getting really reliable signal from subjects. Joe, with the PPU, is that just a management problem that we shouldn't?
Well, I mean, Suzanne posed a question because she said you ran out of digits to actually use the pulse ox, and you were wondering if the ECG could be some sort of stand-in, but it's been our experience, at least on the 7T, that the ECG works fine when you're outside of the magnetic field, but as soon as you move into the magnetic field and the leads are moving sort of as the chest is breathing and stuff, it creates many artifacts, so it becomes somewhat unreliable.
So PPU is more reliable than that. If you have
just using the pulse ox is the most reliable.
But so you need one hand that is still, basically,
or a toe, yeah, or a tongue.
The tongue works.
Tongue works almost, it works really well.
Okay, well, maybe we should do tongue.
Right, Ben's got to go to bed, it sounds like.
Thank you so much, Ben, for joining us. We really appreciate it.
That's great.
Thanks. Sorry, I'd like to stay on, but I hear some voices that are calling me repeatedly. So I better tune out.
Yeah.
Thanks.
Okay,
Nice
good luck with your multi-echo pilots. I'm curious to see how that's going.
Yeah.
All right. All the best. Thanks for asking me.
Thank you.
Bye, Ben.
And I guess we can at least start getting some data and playing with Tadana, hopefully with some help from Suzanne, would be great.
Just register your pilot study for auto bids, and then it will all be taken care of.
Okay.
There are existing data sets that you can play with. I know HY has several data sets because he's acquiring routinely this. I mean, you may just want to borrow it to run through the Tadana pipeline before you start.
Well, he's already, his study is registered for auto bids, so all of his data are automatically run through Tadana and then fMRI prep.
Okay, so I mean, should evaluate that before you just sort of acquire it. We can, once you get a feel for it, because we won't be able to modify the protocol too much from what he's doing, right? He's kind of got an optimal set of multi-echo data. So you can tweak things a little bit, right? You can change the resolution a bit. You can change the TR a little bit. You can change the echo times a little bit, but like Ben said, we're kind of limited with what the overall acceleration, right? Combination of multiband and in-plane is going to be. Yeah, there's not a whole lot you're going to do unless you really, really start getting radical and saying, I want to do 3.5 millimeters isotropic or something. But
I guess the other thing we could do, I think Emily's on the call here. We could try just getting one of our Pac-Man pilot subjects done with the multi-echo as well. The main things I think that we're looking at testing. So HY wasn't looking at motion stuff. So the main stuff we'd want to test would be getting some data where we know we have some motion.
Yeah, in a controlled way for sure. Yeah, I know
how much it cleans it up.
Yeah, he's trying to get a little bit of signal back in the temporal lobe. So.
And with Emily, the question would be, but that's a bit hard to predict. So some of our subjects in Pac-Man are pretty still and some of them are nightmares. So that's one of those cases where you'd actually hope you'd do it on a subject that's a nightmare and be able to clean it up.
Yeah, but going to a voxel resolution of 3.5 millimeters there is totally fine, right? When there's no, I don't know if we have really very high resolution questions there a priori.
Yeah.
But I mean, always at the end of the day, the best way to solve motion is at the front end, not on the back end. So don't be scared to be a little more aggressive with your subjects. Put a piece of tape across the forehead, even under the chin, all these different things, right? I mean, it's nice to set up a subject quickly and everything and get them going on the experiment, but taking a little more time is going to save you a lot of headache on the back.
Well, stopping pulsatile motion in the brainstem may be a baby bathwater situation. I don't think we want to be that aggressive.
No, I'm not. No.
The ways.
Plus, I mean, that's not going to solve Jody's through space problems for when she's got, people moving their hands around and stuff.
No, but you limit the amount of limb motion like we've done. I mean, right? You don't allow people to move from the shoulder. You move from the elbow as far away as possible from the.
I guess that's part of it. Is the thing that we really want is to be able to study more actions that are more sophisticated than that. And so I'm just curious if we can get anything that's better. And the two options, there's only two options I can see to do that. One is something like this in fMRI, but then we have to test, what are the limits of these kind of corrections? And then the other is give up on fMRI and go to FNIRS, which, has its own problems and probably isn't as robust to motion as people say either. But it's just this big hole in cogneuro that you can't do any kind of sophisticated action or, elaborate actions without nixing your signal.
Yeah.
Mm.
And I don't know what your plans are for the phase stuff. It might be cool at some point to see if there's a medical biophysics student or something that might be interested in once we've worked with the multi-echo, comparing them or combining them.
Yeah, for sure. We could look at.
I need to go. Bye.
Thanks, Jorn.
See you, Jorn. We could definitely look at a student. I mean, I'm still looking for students for this fall, so I'll keep that in mind.
Or even doing some of the stuff, which was sort of what we started with Rob Berry, although we didn't get too far with him. It ended up being a fairly simple project, but trying to do some stuff to see how much it would correct the mass motion stuff. So trying something with the bags of saline, and then looking at different approaches for fixing it.
Mm-hmm.
It's also kind of interesting. I don't know how much, I guess people haven't really used it, but I was curious. It would be really interesting to see how much it changes things like multivoxel pattern analysis when you nix all the big vessels. I don't imagine anybody's done anything like that.
Well, that's interesting. I mean, I'm sure it does, but maybe as long as they're consistently nixed, it doesn't matter.
Yeah, I mean, it might be interesting with Brett stuff, to do some stuff with MVPA once he's got the the ocular dominant stuff and see what happens when you clean it up.
Yeah, of course. I mean, the problem for, you know, the ocular dominant stuff is we're not going to be ever using multi-echo. Because
no, but I mean, even just the phase stuff.
Oh yeah, for sure.
If you clean up the big vessels, or you could do something with orientation, like the old Kamatami and Tong stuff with orientation, and what happens to orientation decoding when you kill the big vessels. Does it get better or worse, or because they still don't understand what's driving MVPA at that level of whether it's, you know, it's whether
my feeling
columns or if it's something more global.
I think as long as you get rid of the peel vessels, then anything else that's big, which is really not that big, probably doesn't matter too much. So you might as well just take them and enjoy the extra bold signal you get, more or less, because, you know, there are a couple of 100 micron vessels, or, you know, 100 micron vessels in the gray matter itself. Probably doesn't matter so much for most of this stuff. You know, for some layer dependent fMRI maybe, but I think for the vast majority of stuff, just killing the effect of the big surface vessels is probably all you need. And phase does a great job of that with no penalty, zero penalty.
Okay, well, lots of stuff to try. So I guess in terms of action items, maybe the first thing would be, Suzanne, if we could get some of HY's data and play with Tadana just with that, and maybe.
Yeah, I'll ask him what he has and what he's able to share.
Or if not, we can just collect some new stuff.
Yeah.
And then I'll dig up the old bags of saline on a stick, or we can make some new ones, and then think about collecting some 3T data, and maybe, you know, maybe also doing some at 7T if Jorn wants to try it with the 7T data. And then I guess the other thing, once we sort of have an idea of what we would do with it, then maybe Emily can try a Pac-Man subject with the multi-echo, and we can see, at least if it's a subject that moves a lot, how good it does in real world applications of cleaning it up.
I think I asked you this before, Joe, but my mind or my memory is suffering from age or something. Is there there's a phase option in the multiband?
We can reconstruct the phase, yes.
Even in the case of the multiband multi-echo?
Multiband multi-echo, we can do that with the SVD, with the SVD reconstruction.
Right. Okay. Awesome. Yeah. All right. Well, then we have everything we need to do to play.
Yeah.
And I think the multi-echo, especially a short echo and an optimum echo, could be really helpful for some of Ingrid's studies, even without worrying about, you know, other aspects of the multi-echo, just to recover some of the signal in the auditory cortex areas.
Yeah, that would be great. We lose a lot in anterior temporal lobe. I mean, you know, we see dropout up to the sometimes up to the superior temporal sulcus. Maybe, is that possible? Yeah, that's not ideal. I'm also really interested in brainstem, and auditory brainstem, conveniently enough, is at the same levels as the cerebellum. So I'm going to ask Jorn if, I think in his field of view, the midbrain is included, but we may be able to work together to try to optimize those areas. Yeah, the cochlear nuclei are just inferior to the cerebellum in the midbrain. So.
Are you doing any 7T stuff, Ingrid?
Not doing anything at the moment, but I have fantasies. Yeah, no, I'd love to do auditory midbrain at 7T functional. Yeah, there's a lot that can be done.
Yeah, definitely. You're not doing it just because you can't, it's not easy to get volunteers now, basically?
And I don't have any trainees who are particularly interested in brainstem processing.
Okay, double whammy.
Working on that.
Okay, well, this was great. This reminds me, Ravi, of the good old days when we all used to pile into the journal clubs in the room down on the Cuddy wing with Tudis and David Nicole and Mel and you guys.
Yeah, and only the two of us are not retired. Yeah, no, this is awesome. It's nice to be able to get people like Ben and so on. This is the benefit of Zoom. You know, it has a lot of evils, but being able to have people pop in, you know.
Yeah, he's been super helpful. So I'm sure if we need other stuff too, he's
yeah, I mean, we know him quite well. And
Suzanne, did you capture the chat window?
I basically copied the pulse sequence stuff that Benedict put in.
Okay.
I copied and pasted the Saskia Bowman paper that he mentioned, but I have a PDF of that on my computer, so.
Okay, good stuff. All right, so maybe we can sort of go our different ways and play with some stuff, and once we have a sense of more of how things work and what the data looks like on our system, we might consider doing another one to update people on what we found. Okay, thanks so much, everybody.
Thanks so much for organizing, Jody.
Thank you, especially Suzanne. That was really great.
Yeah, this was awesome. Thanks.
Thanks, guys. Just let me know when you guys are ready to do stuff, okay?
Okay, sounds good.